Hello students, you're welcome to AAE 536 High Speed Aerodynamics. This is the second video lecture, so we'll be starting from where we stopped the last time. That's slide 37 if I'm correct. Yes. So in the last class, we were looking at, in the previous slides, we were looking at the derivation of the governing equations for one-dimensional flows. And then we said an example of such a one-dimensional flow is the flow through a normal shock wave. So moving forward, we'll be looking at the application of such equations to the practical problems of normal shock waves and flows with heat addition and flows with wall friction. In this lecture, we'll be looking at the characteristic Mach number, stagnation conditions of flow, and then we'll be looking at different ways in which the energy equation which we derived in the last lecture can be written. So to begin with, we are going to consider a point A in the flow field as depicted in figure 2.22. Actually, I think I'm just going to switch to this. Okay, yeah. So I think it's much clearer this way. So we look at point A in the flow field, where a fluid element is moving along a streamline, and the fluid element is moving from point A to point B. At that point A, let us, of course, it is traveling with some velocity, and then it has some Mach number. Recall that the Mach number is just the ratio of the speed of an object or the fluid element to the speed of sound in that medium. So the fluid element, we know it's going to have some value of static pressure and then temperature, respectively. So if we now imagine that we take the fluid element and slow it down adiabatically, if it were traveling with some supersonic speed at first, or we imagine that we speed it up adiabatically still until its Mach number at point A is 1. This is just something we are imagining because the fluid element is actually moving with velocity v, and the Mach number is actually defined. But in our own imagination, we are just trying to look at what its properties would be if we slowed it down or if we sped it up adiabatically until its Mach number at that point A is 1. Adiabatically, you know, when you say something, a process is adiabatic, it means it has no energy transfer with the environment. That means no heat addition or no heat subtraction. So as the fluid element, as we are imagining slowing the fluid element down or speeding it up, we are also imagining that such a process is happening adiabatically. That means all the energy contained within the fluid element is still kept with the fluid element as we are slowing it down or speeding it up. As we do this, of course, we know that the temperature of the fluid element will be changing. If it had some temperature T and the point where it was moving with some velocity B, as we are slowing it down or moving it, speeding it up, of course, the temperature will also be changing. So when the fluid element arrives at the point where its Mach number is now 1, still in our imagination, its real the new temperature that it has when in our imagination, when the Mach number is now 1, is noted as T star, as it is on the slide there. So this is just some kind of definition we are making, because the actual Mach number and then the actual temperature of the fluid element is M and T. But we are imagining slowing it down or speeding it up adiabatically to a point where its Mach number will now be 1. And it's at that point, the temperature that it will possess is now defined as T star. So we can also now define an hypothetical speed of sound in such a state as A star, where A star is equal to the root of gamma RT star. You know the speed of sound is just the square of the speed of sound is equal to gamma RT from our previous lecture. So if I just try to make a suitable analogy so that you get the kind of imagination that I want you to have. So consider maybe yourself, maybe at the beginning of the semester, or maybe your parents always give you like 50,000 naira, 50,000 naira per semester, or maybe let me make it 40,000 naira, so that I'll be able to say that if a semester is supposed to have 4 months, that means obviously you have 40,000 naira per semester, and if the semester in a semester if we have 4 months in a semester, that means roughly you're supposed to be spending like 10,000 naira, or you have 10,000 naira per month in the semester. So this is what you know you have, 40,000 naira per semester. But at the beginning of the semester, and the 40,000 naira per semester, imagine, or which is, it might be the case that your parents will only be giving you the 10,000, will only be disbursing the money to you on monthly basis. That means, although you are quite assured that you'll be having 40,000 naira per semester, but you only be getting it at the rate of 10,000 naira per month. So let's say now, okay, we are now in February, but let's say in January, we were given 10,000 naira. Of course, you have to eat, you have to do some other things. So maybe you were able to save. So this is what we call it, amount given. So amount saved. So let's say you were able to save like 1,000 naira, and now we are in February. You've been given 10,000 naira, and now we don't know how much you'll be saving yet. But then you are expecting to get 10,000 naira in March, and then in April you're expecting to get 10,000 naira. At the end of the day, you know you would have gotten 40,000 naira from your parents. So now that we are in February, if you imagine speeding time up until you get to April, that means, let's say, of course, you know you'll be getting 10,000 naira in March, and then 10,000 naira in April. But we are still in February, so you have 10,000 naira, and even possibly less, because you might have had to buy some things already. So, but you are now in your imagination trying to think of how much you will have if time were sped up to April, and without you having to buy anything. That means, let's say you've already spent some money in February and you have like 5,000 left. if you imagine that you speed up time to April, you want to see how much you have without you having to have spent anything. So it will be 5,000 plus 10,000 plus 10,000. That would be 25,000 naira. But then you know that in a month you have to buy things, of course. That means you will not actually have 25,000 naira by the end of April. In fact, you might just have some 5,000 if you're able to save some money there. You might have maybe some money saved, but you will not have up to that amount. But you're just trying to imagine how much you have if you speed things up and without you having to spend anything. So think of the spending now as a means of, if you like, energy or money transfer from your hand to other means. So the same way a fluid element, so the same way we said the fluid element is moving in a flow, traveling from point A to point B. So at this point, it has some value of velocity, just like you also have some allowance that your parents give, and then of course you can also describe its Mach number and then talk about its temperature and then pressure, right? So if you now assuming the fluid element is moving at a speed which is less than the speed of sound, then its Mach number is less than 1. If we imagine that we speed it up, still at this point, we speed it up to Mach 1, then of course, just like we were imagining here, if we speed time up to April, then the amount of money you'll be having in that imagination will not be 10,000 in February, to be around 25,000. So the same way, we imagine we are speeding up. Let's look at the first instance where we are speeding it up. So it was traveling at a Mach number less than 1. So we are now speeding it up to Mach equals 1. Obviously, the temperature will have changed when you are speeding it up. So because the temperature will have changed. So we can also try to, if it's traveling at a speed where the Mach number is greater than 1, we can also imagine a process whereby we are slowing it down. Just in our imagination, we are slowing it down until its Mach number is now 1. So at that point in time, which is just an imaginary point in time, we can now define the temperature to have at that point as T star. So this is just an imaginary temperature that it will have. It might never have this value of temperature, because if it's going to be slowing down, it's most likely it will be slowing down in a non-adiabatic process. If it's going to be speeding up, it's most likely it's going to be speeding up in a non-adiabatic process. Well, now in our imagination, we are assuming that it is doing that adiabatically. That means all the energy that it possesses is not allowed to exchange with the surroundings. So the fluid element is allowed to keep all its energy as it's being sped up or it's being slowed down. So the temperature it has at that point, at that imaginary state, is T star. Immediately that we define T star, we can also go on to define a speed of sound associated with that imaginary state, and it's just going to be equal to the square root of gamma R T star. So I hope this is clear enough to you, and I hope I haven't confused you with this analogy I've been trying to make. So just imagine you have you know the amount of money you are supposed to be getting like per semester, but you're not at the end of the semester yet. So if you were supposed to be given 40,000 naira, in fact, at the end of the semester, you will not even have 40,000 naira because you have spent some things. So that is also analogous to what I said before, that if the fluid element is going to be sped up or slowed down, it will not, in the real sense, it will not do that, or in that process cannot go on without it losing or gaining some kind of energy. So the same way, if you try to go forward in time, or by the time it is April 2, you will have spent some part of the allowances that you are given. So you won't actually have 40,000 naira by April because you would have spent some money out of the allowances. So at the same time, by the time it's April, if you try to look back in time and think of how much money was there at the beginning of semester for you to spend, it will be 40,000 naira, but that is just an imaginary situation that you are imagining. The actual real process is different, or the actual real situation is different from what you are imagining. But now it is going to be useful for us to define such an imaginary state where the fluid element has been sped up or slowed down to Mach 1, and then we define the temperature it has then as T star, and then the speed of sound at that point as A star, which is equal to gamma R T star. So if we go back to the slide now, I think I want to do the slideshow. So that is the explanation for T star and then gamma R T star. So therefore, for any given flow with a given Mach number and temperature at some point A, we can associate with its values of T star and A star at the same point as defined above. We will be looking at the means of calculating T star and A star later on. In the same sense that we just defined an imaginary state where the Mach number of the fluid element is 1, we can now also imagine that we slowed, with the fluid element is moving, and then we try to slow it down isentropically to the point where its velocity is now 0. Isentropically, that means the process I'm talking about is both adiabatic and reversible. That means all the energy that the fluid element possesses at the point in time that we want, we start moving it, slowing it down to 0 velocity, is still kept with the fluid element even at the point where it gets to 0 velocity. So at that point, it's still in our imagination that it attains the velocity of 0. That state is called the stagnation state, and the value of pressure to have then is termed the total pressure. The total pressure, and it's we denote it by P naught. And then the value of temperature it will have at that point in time, or at that point in our imagination, is we term it T naught. So P naught, T naught. You can usually, they can also be called stagnation pressure and stagnation temperature, respectively, as the textbook says. Stagnation and total they mean about the same thing in this sense. And then there are actual properties associated with the fluid element while it is in actuality moving at velocity v with an actual pressure and temperature equal to P and T respectively. So even though the fluid element is moving with some real value of pressure and then some real value of temperature, we can associate with it at that point that is still moving some stagnation properties like the stagnation pressure and then stagnation temperature. At that point in time too, we can also associate with it the speed of sound. You see, we'll name it very soon. The speed of sound that it will have, assuming it will slow down or sped up to Mach equals 1, and that speed of sound is called is denoted as A star, and then the temperature that it will have, if it were slowed down or sped up adiabatically in our imagination to when its Mach number will be equal to 1, then the temperature at that point is denoted as T star. So this is probably too small for it to see. I'll go back to the normal slide. So as you see from here, using the above definitions, we can introduce other parameters as follows. The characteristic Mach number, M star. M star is just the ratio of this actual speed of the object to the characteristic speed of sound. That means the speed of sound of the condition when the fluid element has been imagined to be slowed down or sped up to Mach equals 1. So we can also define the stagnation speed of sound as A naught equals square root of gamma R T naught. Then the total density is also equal to P naught over R T naught. So we move forward. Yeah. So now we having defined such conditions and such flow properties, we move on to see the alternative forms of the one-dimensional energy equation. So looking at equation 3.9 there, which is the energy equation for one-dimensional flow. If you assume that there is no heat addition, that means if you assume an adiabatic flow, then the Q term will go to 0, and then what we just have is equation 3.21. That is just the statement of the conservation of energy. H1 plus U1 squared over 2 equals A2 plus U2 squared over 2. The specific enthalpy plus the specific kinetic energy in the first state is equal to, is constant. So the total energy in the first state is equal to the total energy in the second state. So, but we remember that for a calorically perfect gas, the specific enthalpy is just equal to the product of Cp and T. That means we can substitute for specific enthalpy in equation 3.21. That means just put Cp in place of H in this equation. That means we have Cp T1 plus U1 squared over 2 equals Cp T2 plus U2 squared over 2. That means going from in this one-dimensional in figure 3.5, which we saw in the previous slide, going from the fluid element is going through the shock wave. So going from state 1 to state 2, the energy is conserved. We just assumed that there is no heat addition because we are not directly heating. If we consider that the shock wave is on an aerofoil or a moving body inside the atmosphere, we are not directly heating up the flow around the air, the body moving through the flow, and we are not directly taking heat away from it. So actually, the flow around such an object in that condition is actually adiabatic. So the assumption that Q is 0 is actually valid, more or less. So So yes, this is equation 3.22 is an alternative form of the energy equation. But we also know that Cp equals gamma R over gamma minus 1. And I'll show you why that is true. So if we start from the equation at Cp, that is the specific heat at constant pressure, minus Cv, the specific heat at constant volume, equals R, that is the specific gas constant. So if you try to, so now we are trying to find an expression for Cp in terms of R and then gamma. Gamma is just the ratio of the specific heat, so Cp over Cv. So if you try to divide through by Cv, let's start with that. We divide through by Cv, divide through by Cp, so that we have 1 minus Cv over Cp equals R over Cp. And we know that Cv over Cp is just the inverse of gamma. So that means we have 1 minus 1 over gamma equals R over Cp. Then from here we know that gamma into gamma minus 1 equals R over Cp. That means Cp, of course, then is equal to gamma R over gamma minus 1. So now our energy equation, which we have Cp(T1) plus U1 squared over 2 equals Cp(T2) plus U2 squared over 2. So we can substitute gamma R over gamma minus 1 into this equation. And then when we do that, we have gamma R T1 over, that means I'll put in Cp here, over gamma minus 1. So this is Cp there, plus U1 squared over 2 equals, so I'll just substitute for Cp there too, 2 over gamma minus 1 plus U2 squared over 2. So what can you notice from here? I wish you could answer me. So anyway, we see already that, or if we recall that A squared equals gamma RT. That means in this equation we can make some kind of substitution for gamma RT. So particularly over here and over there. So we can now see that A1 squared, that means A1 squared is gamma RT1 over gamma minus 1 plus U1 squared over 2 equals A2 squared over gamma minus 1 plus U2 squared over 2. So we see that we started with some form of energy equation like this: H1 plus U1 squared over 2 plus Q equals H2 plus U2 squared over 2. That is the form that we started with, and with our assumption of no heat addition, Q went to 0, and then with our noting that Cp equals gamma R over gamma minus 1, we got this equation, and then with our knowledge that A squared equals gamma RT, they are now in this equation. But we also know that if we use the equation of a perfect gas, equation of state, that means P equals rho RT. This implies that RT is just equal to P over rho. That means we can actually, instead of substituting A squared for gamma RT there, we can actually do something like this, put in P over rho for RT in the equation there. So we have gamma P1 over gamma minus 1 rho 1 plus U1 squared over 2 equals gamma P2 over gamma minus 1 rho 2 plus U2 squared over 2. These equations are equivalent and saying the same thing. They are equivalent. So we'll see why we are making this. We are making these alternative forms of the energy equation. They will be very useful later on. So that's how we got equation 3.23, and then equation 3.24. That's how we got it, and then equation 3.25. So note that the equations so far have been written for a flow with no heat addition. That is, we assumed an adiabatic flow where Q equals 0. So if we now return to the defined flow properties, that is the characteristic state where we imagine that we slowed the fluid element down or sped it up to the condition where its Mach number is not equal to 1. And then that's the first imaginary state that we talked about. And then the second imaginary state was when we slowed it down isentropically to the point where its velocity is equal to 0. So we are going to now try to apply write the different forms of the energy equation which we just looked through. We are going to use it for the real state and then the imaginary state. So if we do that, keeping this is the equation written for the real state. So the real state is on the left hand side, and then the imaginary state is on the right hand side. So in the real state, the velocity of the object or the fluid element is u. So the kinetic energy, the specific kinetic energy is just u squared over 2, and then that's the speed of sound in the real state. In the imaginary state, we know we defined a characteristic speed of sound, h star, so h star squared over gamma minus 1, plus we know that at the imaginary state, we said its speed then is also going to be equal to a star. So its speed is going to be equal to a star because we said at that imaginary state that the speed of the Mach number is equal to 1. So if Mach number is just the ratio of v over a, so that means the speed of the object at that imaginary state is also going to be equal to the speed of sound. So anyway, combining it, we see that there is a way for us to calculate the characteristic speed of sound from the knowledge of the flow the properties of the fluid, and then the velocity of the flow velocity of the velocity of the flow, and then the speed of sound in the real state. So moving forward, we recall that in the stagnation state, the velocity is going to be equal to 0. So if we write the energy equation between the real state and then the stagnation state, this is what we are going to have. Let me just switch to the computer screen so I can write and see what I'm saying. So what we just talked about, this is real state, and this is imaginary state. So in the real state, it has M and V, C, P, and rho. In the first imaginary state, its Mach number is equal to 1. Its temperature is T star, and then its characteristic speed of sound is A star, and then the characteristic Mach number is V over A star. At this point in time, the imaginary state, since we said its Mach number is equal to 1, that means the velocity to have then is 1 equal to, the Mach number is 1 equal to V over A star. That means its velocity is just going to be equal to A star. So if we write, so this is the process, we imagine the process to go adiabatically. So if we write the one-dimensional energy equation in this form, for these two states. So since we are going from the real state to imaginary state, we just drop this subscript for the real state and know that this is the real state. So it has a speed of sound there too. And then we just keep the asterisk for the imaginary state. So since here, over here, I said the velocity is A star. So this is just also going to be A star squared. So, and then by the time we do the simplification, we get the equation that we saw on the slide. So now we are going to the second, so this is the first process. We are going to the second imaginary state where the velocity is now equal to 0. The temperature is T0, the pressure is P0, and then the density is ρ0. That is the stagnation condition. So if we try to write this kind of equation for the stagnation condition, that means going from real state, so real state, stagnation state, so going from there, we noted that we will be doing that isentropically. So we can write this form of energy equation for that process. So if we write it, then we know sorry, not this form. We can, of course, we can still write this form too, but what we're looking on the slide is CPT plus U squared over 2 equals CP T0 plus u naught squared over 2. But what is u naught? It is equal to 0. So this is off. So we have CPT plus u squared over 2 equals CPT naught. So that's how come equation 3.2 was derived. So if we divide through by CPT, so divide equation 3.27 by CPT, then we have C naught, so we divide by CPT, CP is carry cancel, we have T naught over T, and this goes to, turns to 1. So we have T naught over T equals 1 plus C squared over 2 CPT. Then we can make the substitution for CP. You know, CP is equal to gamma R over gamma minus 1. And then we can make substitution for gamma RT. That is gamma RT equals A squared. So then you see this is U squared over A squared. That means we can make a substitution for that. U squared over A squared is just the square of the local Mach number. They are supposed to be squared over this ratio U over A. So when you make all those substitutions, you notice that this is just the square of the Mach number. So at the end of the day, we have this ratio T naught over T equals 1 plus gamma minus 1 over 2 Mach times Mach squared. But we can recall the isentropic relations, equation 3.29 from the last class. So since we have an expression for the ratio of the stagnation state to the real state for the temperature, that means we can directly use this relation between the pressure ratio, density ratio, and temperature ratio to get the density ratio and then the pressure ratio. That means we're just going to put this in for T naught over T inside this equation, and that's how come you get equations 3.30 and 3.31. That means for any given value of or for a fluid element traveling at some with some flow velocity where the Mach number is known and then the local temperature is known, we can directly calculate for the stagnation temperature, and then from all this we can also calculate the stagnation pressure as well as the stagnation density. So moving forward, you can also note that we can write this for the stagnation state too. Again, at the stagnation state, the velocity is equal to 0, so the other part here is 0. So if we write it in this form, if we go, so this is for the stagnation state, so equation 3.32. But if we go like 2 slides back, we see this equation 3.26, which we wrote for the characteristic state of the fluid element. That means that imaginary state where it has Mach number equal to 1. So that means this is equal to this, and then over here, that is still equal to this on the left hand side. That means we can actually equate A naught squared over gamma minus 1 to all this over here. And with that, we can find a ratio between the characteristic speed of sound and the stagnation speed of sound. And since the speed of sound is related to the temperature, that is A squared is equal to gamma RT, and it's this ratio here also gives the temperature ratio between the characteristic state and then the stagnation state. So T star over T naught is equal to 2 over gamma plus 1. Immediately we have this ratio, we can plug it into the isentropic relations and use it to find the ratio of the pressure at the characteristic state to the pressure at the stagnation state, and is equal to, so of course P star over P naught is equal to that, and then immediately you can also calculate for the rho star over rho naught. So we can notice from here that this ratio are only dependent on the property of the fluid gamma. So for air at standard condition, the value of gamma is equal to 1.4. So that means we can, if we insert 1.4 there, we can find the numerical value for this ratio as well as for this and that ratio. So J star over T naught is equal to 0.833, P star over P naught equals 0.528, rho star over rho naught equals 0.634. And they are useful numbers. You should try to keep them, let them be at your fingertips. They are quite useful and will be used quite often. So yeah, if we divide equation 3.26 by u squared, like you're seeing on the slide, then we can find a relation between the real Mach number and then the characteristic Mach number. So the real Mach number and the characteristic Mach number. And then we can try to make the observations on the next slide that when n star equals 1, or m star is going to be equal to 1, m star is going to be equal to 1 only if the real Mach number itself is equal to 1. You can plug it into, you can try it on your own. It takes just a few steps to see it. M equals 1, we only make n star equals to 1. And then when m star is less than 1, m is also less than 1. That means when the characteristic speed of sound, characteristic Mach number is less than 1, when it is subsonic, that means the real Mach number is also subsonic. When the characteristic Mach number is supersonic, the real Mach number is also supersonic. But something interesting happens when when the real Mach number goes to infinity. The characteristic Mach number approaches some finite value, and what we are saying here is a Mach number going to the very, very hypersonic regime, maybe as hypersonic as it can get. So for this to go as high as possible, we know this, if this is tending to infinity, then this denominator over here should be going to 0. As you know, any number divided by 0 gives infinity. That means if we want this to tend to infinity, we should then equate this to be equal to 0. When you equate this to be equal to 0 and solve for m star, you have this value for m star as m tends to infinity. So that means it is quite useful for us to use when m is tending to infinity, going to a very, very large value. This is only going to tend to some finite value, which will be used for calculations as we progress. All the equations in this section, either directly or indirectly, are alternative forms as you've seen. There are alternative forms of the original and fundamental energy equation for one-dimensional adiabatic flow. Make sure that you examine the equations and you feel very comfortable with them and with the ways they've been derived. I think that is the end of this slide. yeah, it's the end of this slide. In subsequent lectures, we'll be looking at the application of all that we've learned so far to the calculation of flow properties across a shock wave. And I certainly do hope that we have the time to apply these equations to the flows with heat addition, and one-dimensional flows with heat addition, and then one-dimensional flow with wall friction. So this is the end of the video lecture for today, and when you have watched this video, I hope you send me your feedback, your comments, and then your questions. Remember to send feedback, comments, and then questions. Thank you.